once you understand the fundamentals of finding probability, you're ready to move on to rules for combining probabilities. What we mean by this is types of events where we're looking for the probability of something and something else, or something else. One example would be drawing a card from a deck, and we want to know what is the possibility that that card is a queen and a club, or the queen of clubs. And as we'll see, the rules for combining probabilities like this all just involve multiplication or addition. So let's start with probabilities that involve the word and. Now it might be that we're dealing with independent events or dependent events. So let's begin with independent first. And the rule, as we'll explain why in just a minute, is that you would just find the probability of each event and then multiply. All right, so and would mean multiply. So as an example, find the probability that a 100-year flood, which is a flood with a 0.01 probability of occurring in a given year, will hit the same city in 2 consecutive years. Assume that a flood in 1 year does not affect the likelihood of a flood in the next year. So that last sentence is the clue that's letting us know that these events are to be considered as independent for this example. All right, so what is the probability that the flood would happen in the first year? Well, that's 0.01. Right, and then the probability that it would happen in the next year, ignoring the previous year, would still be 0.01. And then we can multiply those to find the probability that the flood would occur in those 2 years. And that's 0.001, 3 zeros and a 1, or 1 in 10,000. Okay, so why do we multiply? Well, if you think back to the way that we counted the numbers of outcomes, this may make sense. So let's draw this one out. So let's say we want to find the probability, let's say we're rolling a die, and let's roll it twice. Okay, so what's the probability that we would get a number less than 3 the first time, and then get an even number the second time? All right, so if I write this out, when I roll the die the first time, we would get options 1 through 6. All right, it's going to be one of those options. And then for each of those outcomes, I can pair that with the outcome for when I roll the die again. All right, so when I roll it again, it's independent of what happened on the first roll. Right, so it could still be 1 through 6. So if I roll a 1 the first time, then it could be 1 through 6 and so on. And we've seen this before. Let me redraw this going sideways for a little more space. Okay, so I've drawn out all of the different outcomes now. And then if we look at these and we look at the probability of getting a number less than 3, all right, well, let me just circle the outcomes that represents. So the numbers less than 3 on the first die would be 1 and 2. All right, and then the probability of getting an even number when we roll the die again. Right, so now I'm assuming that the first number was less than 3, and now I'm only going to look at these outcomes and then move on from there and see which options are even on the second roll. Okay, so we've got 2, 4, 6, 2, 4, 6. All right, so the probability, we know with the multiplication rule, this is supposed to be the probability of the first thing, getting a number less than 3, right, which is 2 out of 6. There's 2 out of 6 ways to do that, or we could say 1/3 if we reduce that. And then the probability of getting an even number, all right, well, when we roll it again, out of 1 through 6, 3 of the numbers are even. So there's a 3 out of 6 probability, or 1/2, right, that that number will be even. And then multiply, and that's 1/6. Now, if you look at what we've circled here in blue, you should see that out of all of the different possible outcomes represented by all of these numbers at the ends of the branches here, we have circled exactly 1/6 of them. Or you could even think of this as percentages or proportions, right? So I took a third of the numbers by circling 1 and 2, and then I took half of those numbers by circling just the evens. And we've seen this before with percentages. When you try to take percentages of something. Of means multiply. So this is just another example of using multiplication to represent portions or percentages of things. I found a few more examples online, and I'll post the link to this Math Stack exchange, and you can look through these few answers. But other people have had the same question: why do you multiply when you're finding probability of independent events? Right. So another example: suppose the probability of a person being left-handed is 1/10, and the probability of being blue-eyed is 1/3. The intersection of the events left-handed and blue-eyed is left-handed and blue-eyed. So that's what we mean by and. It's an intersection. It's two things, left-handed and blue-eyed. If the events are independent, right, they don't depend on each other, then the proportion of blue-eyed people among the left-handed people is the same as the proportion of blue-eyed people among the whole population. Right. So this is a something that's built into the meaning of independent. All right. So we can assume that these probabilities should be the same among the whole population as they are among whatever category that we're considering, right? And of course, this is on average. If you draw a certain sample of left-handed people, then maybe you wouldn't see exactly that. But for calculating theoretical probabilities, you may assume that this is true. All right. So thus, the same proportion, a third of them, right? So thus a third of 1/10, right? A third of the 10th. So the 1/10 is the people who are left-handed, and then the third is the blue-eyed. Okay? And again, to find a third of 1/10, you multiply. So a 30th of the population should be left-handed and blue-eyed. And then a second example here dealing with pizza. So half the slices have anchovies, represented by A, and we are going to select a third of the slices independently of whether or not they have anchovies, right? Then the anchovy slices that you have are 1/6 of all the slices of pizza, right? So again, this depends on the events being independent. So theoretically, if half of them have anchovies and you close your eyes and randomly take a third of them, then out of that group of, the third that you picked, half should have anchovies and half should not, right? And again, half of 1/6 is, half of 1/3 is 1/6. All right, so if you were wondering why we multiply probabilities, I hope that helped. If you weren't and you were thinking, well, that just makes sense to me, then move along. All right, let's consider an event that is not independent, right? So we would look at two events that are dependent on each other. So for example, a 3-person jury must be selected at random from a pool that has 6 men and 6 women. What is the probability of selecting an all-male jury? All right, so the events that we're considering here are choosing 3 people. So for our first person, we want them to all 3 be male. So what's the probability that the first person is male? Well, we have 6 men out of 12 total people. So there would be a 6 out of 12 probability that the first person is a male. Now, when we get to the second person, we're choosing from the same pool. And a lot of times that's what makes events, that's what causes them to be dependent, right? Is if you're choosing from the same group, then by that very act of picking something the first time, it does affect the options that are left, and it changes the probabilities. All right, so now assuming that the first person we picked is male, right, then now we're down to 5 men and 6 women, right? So now the probability of the second person being male is only a 5 out of 11 chance. Okay, so we're down to 11 people to choose from. And then for the third person, once we've picked 2 males, now we're down to 4 men and 6 women. So there's a 4 out of 10 chance that the third person will be male. Right? And then as we saw just before, we can still multiply. Right? So anytime you're finding the probability of an event involving and, it always does mean multiply. Right? You just have to worry about, is it the same number you're multiplying, or do you need to modify it if the events are dependent? Okay. So multiplying, we get 120 over 1320, which is about 0.091. All right, so there's about a 9% chance that we would get an all-male jury.